I will be dealing with the chapter equilibrium. In this chapter, we will be discussing regarding concepts related to equilibrium constant. We will see how to calculate the equilibrium constant in terms of concentration, in terms of pressure. We will also discuss the relation between Kc and Kp, that is equilibrium constant in terms of concentration as well as equilibrium constant in terms of pressure. We will be discussing Le Chatelier's principle. We will also deal with some concepts related to ionic equilibrium, which includes calculations related to pH, pOH, buffer solution, solubility product, even predicting whether a precipitation takes place or not under certain conditions. These are the things that we will be dealing today, guys. When I say equilibrium, the one thing that strikes your mind is an object that is under the influence of two opposing forces. This is possible in the case of chemical reaction also. A chemical reaction can be in a state of equilibrium under the influence of both forward as well as backward reaction, which take place at an equal rate. Equilibrium is a state that is possible only in the case of a reversible reaction. So what are these reversible reactions? Reactions can be classified into two types. One is reversible, the other one is irreversible reactions. Reversible reactions are the reactions which can be reversed, that is the product formed, they give back the reactant under same conditions of temperature and pressure. Whereas irreversible reactions are the reactions which cannot be reversed, that is the product formed do not give back the reactant under the same conditions of temperature and pressure. Equilibrium can be attained only in the closed vessel. In an open vessel, the product formed will not give back the reactant. So equilibrium is a state that is possible only in the case of a reversible reaction, where the rate of forward reaction becomes equal to a rate of the backward reaction. It is experimental fact that reactions carried out in a closed vessel, they initiate. As the time passes, the rate at which the reaction takes place slowly decreases, and after some time it appears to have stopped. But actually it doesn't stop. The products formed, they start giving back the reactant at the same rate. That is, the rate of the forward reaction becomes equal to the rate of the backward reaction. Hence, the reaction appears to have stopped, where the concentration of the reactant and product does not change with the time. But actually the reaction will be occurring in both the direction, but the speed at which the conversion takes place will be same. Hence there will be no change in concentration of reactant and products with the time. There are certain characteristics of equilibrium, that is equilibrium is dynamic in nature, that is the rate of forward reaction will be equal to the rate of backward reaction, that is the reaction will be occurring in both the direction, but the rate at which both the reaction occur will be same. With the time, the concentration of reactants and products does not change. The position of equilibrium is not affected by adding a catalyst, but change in concentration, change in temperature, change in pressure affects the equilibrium. It favors the equilibrium to take place in one direction, hence it shifts the position of an equilibrium, whereas a catalyst does not change the position of equilibrium, it only helps the equilibrium to attain faster. So students, we will see today how to calculate the equilibrium constant in terms of concentration as well as in terms of pressure, and then we will solve some related problems. Consider a reaction A into A plus B into B in equilibrium with C into C plus D into D, where the capital A, capital B, capital C and capital D are the reactants and products, whereas small a, small b are the coefficients with respect to the reactant, and small c and small d are the coefficient with respect to the product. So hence equilibrium constant for this reaction is given by the expression equilibrium constant in terms of concentration Kc is equal to concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A divided by concentration of B raised to B. That is, equilibrium constant is the ratio of product of concentration of the product to the concentration of the reactants raised to the powers, and powers are equal to the stoichiometries as per the balanced chemical equation. Even you can write the equilibrium constant in terms of pressure. Equilibrium constant in terms of pressure, Kp is equal to pressure of C raised to C into pressure of D raised to D divided by pressure of A raised to A into pressure of B raised to B, provided where A, B, C and D all should be in their gas phases. So these are the two equations to calculate the equilibrium constant in terms of concentration as well as equilibrium constant in terms of pressure. Now we will solve some problems related to this. Students, let's deal with the first question. 4 mole of sulfur dioxide and 4 mole of oxygen are allowed to react to form sulfur trioxide in a closed vessel. When the equilibrium is reached, it is found that 25% of oxygen is used up. The total number of moles of all gases present in the vessel is. So the options are option A 7, option B 6.5, option C 2, option D 8. In this question, we need to find the number of moles of all the gases that are present at equilibrium. For this, what we need to do is we need to write the reaction first, initial number of moles they have given, then we should go for the number of moles reacted, then the number of moles of all the gases that are remaining at equilibrium. Let's start the solution, students. 4 moles of sulfur dioxide and 4 mole of oxygen are allowed to react. So this is a reaction between sulfur dioxide and oxygen to form sulfur trioxide. Let us balance the question first. Now, equation 2. Now the equation is balanced. 2 sulfur, 6 oxygen, 6 oxygen. Let us see the initial moles they have given. Initial moles they have given. They have given you 4 moles of sulfur dioxide, 4 moles of oxygen, and moles that have reacted. They have said that 25% of the oxygen is used up at equilibrium. That is, if we consider 4 moles of oxygen, then 25% of oxygen refers to 1 mole of oxygen. That means according to them, the moles reacted is 1. If you look at the equation, if 1 mole of oxygen reacts, at the same time 2 moles of SO2 reacts. So the moles of sulfur dioxide that has reacted will be 2. Then the moles of product that is formed there. No. Product formed. If you look at a balanced chemical equation, if 1 mole of oxygen reacts, you get 2 moles of sulfur trioxide. So they have mentioned that 25% of oxygen is used up. That is, the initial number of moles is 4. So 25% of 4 mole refers to 1 mole. So we have taken 1 mole of oxygen is used. If 1 mole of oxygen reacts, simultaneously 2 moles of sulfur dioxide reacts. Hence 2 moles of sulfur dioxide reacts. If 1 mole of oxygen reacts, then you get 2 moles of sulfur trioxide. So the moles of sulfur trioxide formed will be 2. So we need to calculate the number of moles of all the gases that are present at equilibrium. Let us see what is the number of moles that are remaining. Number of moles remaining at equilibrium. We had taken 4 moles of sulfur dioxide, out of that 2 moles reacted. So the number of moles remaining is 2. We had taken 4 moles of oxygen, 1 mole of oxygen reacted. So the number of moles of oxygen remaining is 3. So 2 moles of sulfur dioxide is formed that remains in the reaction vessel. So the total number of moles at equilibrium is equal to, it is 2 moles of sulfur dioxide plus 3 moles of oxygen plus 2 moles of sulfur trioxide. So that will be equal to 7 mole. Hence option A is the right answer.
ಡಿಯರ್ ಫ್ರೆಂಡ್ಸ್, ನೀವು ದೀವಿಗೆ ಯೂಟ್ಯೂಬ್ ಚಾನಲ್ಗೆ ಸಬ್ಸ್ಕ್ರೈಬ್ ಮಾಡಿ, ನಿಮ್ಮ ಫ್ರೆಂಡ್ಸ್ಗೂ ಹೇಳಿ, ಇದೇ ಥರ ನೂರಾರು ವೀಡಿಯೋಸನ್ನು ಫ್ರೀಯಾಗಿ ನೋಡಿ.